Hello and welcome to the video solutions here for paper 3 as part of set C, right? As we can see here on the screen, so this is the very last paper then as part of set C. So this here is the applied paper, right? So stats and mechanics, 50% stats, 50% mechanics, right? So 50 marks for each section. I've got a few points to make here, right? So let's see if I can get this in the correct order. Now, normally I wouldn't include the large data set here part of the mock exam paper. So for set A and set B, we didn't include anything on the large data set. However, for this year's paper, I have decided to include the large data set. It is just a few marks, right? Nothing too intense, but to try and make this, feel as kind of realistic and similar to the actual Edexcel papers, like I said, I have included the large data set. As painful as that is, I agree with many students, it's painful, but there we go. Again, all this good stuff, right? So this practice paper closely follows the Pearson Edexcel specification for A-level maths. However, Pearson Edexcel have no affiliation to this paper and are not responsible for any of the material featured in this paper. As we mentioned before, there are two sections in this paper, so answer all the questions in section A being stats part, and then all the questions in section B. Again, section B, right, being the mechanics part of the paper. And again, you can use your formula book, but you should already be familiar with all of this. You can use the calculator, and again, you get 2 hours to complete this paper. There's 12 questions for this paper here, and again, the total number of marks for the paper is 100. Other than that, I don't think there's anything else to really say here. If you are looking for additional revision here, don't forget we've also got set A, paper 3, and also set B, paper 3. Please go and check that out if you are looking for any more revision here for mechanics and stats. I've also had many questions asking, do we do individual revision videos for topics within stats and mechanics? And yes, we do. I'll leave a link to those in the description down below. So I'll give you the kind of links there to the respective playlist for all of the topics here within stats and mechanics. Other than that, though, I'm kind of just yapping here at this point. So let's not waste any more time then, and let's just get started here then with question 1, right? The stats part of the paper. So for the first question here, question 1, we have a very typical stats type question, right? As we can see, then we've got some data here. We've got a load of waffle to go alongside the data, and then a few different parts to the question. So let's just break this down then step by step here. So for the first part of this question, part A, we've got 2 different parts, right? We've got part 1 and part 2, but before we answer this here, or attempt to answer this here, let's just quickly read the question. So what we've got here then is a sports scientist that believes that there is a relationship between the stride length, L centimeters, and the sprint speed, B meters per second, of elite female sprinters. A random sample of 10 athletes is taken and the relevant data is shown in this table here. The sports scientist plans to use a linear regression model based on these data and interpolate or extrapolate as necessary to estimate the sprint speed of other elite female sprinters based on their stride length. So for the first part of this question, then part A, like we said, right, there's 2 different parts. So for the first part then, part 1, what do we want to do here? So we want to briefly explain what is meant by extrapolation. Now, this part here is just a definition, right, that you need to be familiar with. So extrapolation then. So extrapolation, let's write this down in full. So extrapolation is when we make predictions that are outside the range of the data, or outside the data range, right? Whichever way you prefer to kind of describe that. So extrapolation is making predictions. So making predictions outside the range of the data, okay? And that's all we need there, right? This would just be 1 mark, so outside the range of the data. Perfect. Okay, that gets us the first mark there. And then for the final mark here of part A, so this is part 2 here, it just says, explain the dangers of extrapolation. So why might extrapolation here not be a particularly good idea? Well, what we say then is extrapolation can be unreliable as the trend may not continue. So I'll just say here then that this is unreliable. So this is unreliable as the trend may not continue. Okay. And there we have it then. So that's all we need there for part A. So what we're told here then is a sports scientist attempts to calculate the product moment correlation coefficient R and obtains a value of 1.5. So for part B then, it just says here, without carrying out any further calculations, explain why the product moment correlation coefficient must be incorrect here. So why is this value then of 1.5 here for the PMCC incorrect? Well, for part B then, you should be aware here that R, so R here, let me just rewrite this. So R here is between -1 and 1, right? So if I've got R is equal to 1.5 here, then clearly that's greater than 1. So 1.5 is greater than 1. So therefore, the PMCC here must be incorrect, right? So therefore, the PMCC is incorrect. You don't need to go into a massive amount of detail, right? Just kind of obviously explaining that 1.5 is greater than 1, and therefore this cannot be PMCC. Okay, so there we have it then. That's the 1 mark there for part B in the bag. Now for the next part of this question, then part C, all we want to do here is use our calculator to evaluate the product moment correlation coefficient. And again, it's just 1 mark here, but we are just simply using our calculator. It shouldn't be anything too intensive here in finding the PMCC. So for part C then, how do we actually do this here? By using our calculator. So I'm hoping this is pretty trivial for most of you watching this video, but just in case that you're not too sure how to do this, let's just quickly run through how you would find the PMCC by using your calculator. So obviously the first thing that you need here is a calculator that can find the PMCC. If you don't have that, then please do go and get a calculator quick before the exam. It will just save you so much pain as you work through the stats part of the applied paper. So obviously the first thing that you need to do here is make sure that the calculator is turned on. We're not going to get far without the calculator being turned on. So I go to the main menu here. So what I want here then is stats mode. Now, it doesn't matter, by the way, if you don't have a calculator, just go on something like, I don't know, Amazon or eBay or something like that, right? Or Facebook Marketplace. Just get an old graphical calculator. It really doesn't matter. My calculator here is, I think it's close to like 15 years old, which is pretty old, I guess. In terms of calculators anyway, that's nearly as old as some of you sit in this paper, which is quite crazy. And I think it starts to show how old I'm getting now. But I digress. So anyway, I go to stats mode. And once I do that, I get a few different lists here. So I get list 1, list 2, list 3, list 4, so on and so on. So what I want here then is list 1 and also list 2. Okay. Now, in list 1 then, what I'm going to input here is the values of L, right? So that would be 155, 160, 172, so on and so on. Okay. And I keep going here then to the very last value of L here, which is 172. Perfect. Okay. Just extend that down here. And now for list 2 then, just basically repeat this here now, but with the values of V, right? So 9.2, 9.3, 9.7, so on and so on. Again, up to the very last value here for V, which is 9.8. Perfect. Okay, so input those into your calculator. And once you've done that then, what I need to press here is calc. So I press calc here. I then get 3 options on my calculator anyway. I get 1 var, 2 var, and reg. So reg here just means regression. So that's what we want, right? So regression or reg. I press that and I get quite a few different options here because for regression, we have different regression models. I've got linear regression, quadratic regression, exponential regression, so on and so on, right? But what I want here then is just linear regression. So I just press X here, which on my calculator is the first option. And once I press X here, I get 2 different options here. I get AX plus B and A plus BX. Now, we just want the value of R here, so it really doesn't matter which you choose. I just choose A plus BX out of habit, but either's fine. So a plus bx. Okay. And once you press this then, I get a few different things here. I get a, I get b, I get r squared, MSE as well. Now, the only thing that we're actually concerned about here is the value of r, right? R being the product moment correlation coefficient. And in this case here then, if you do this correctly, what you should find for r is, so we get 0.9225976. Okay. And if I round this here then to say 3 significant figures, what I get here then is 0.923 there. Okay. And there we have it then. Now, just a quick point here. You do not need to show all of this here. You could just simply give the value of r, and that's just the one mark there, right? But all I'm trying to do here then is just demonstrate how we can use our calculator here to find the PMCC. So hopefully that helps. Now for part D then, so for part D here, what does it say then? So it says, stating your hypotheses clearly, test at the 1% significance level whether or not there is evidence that the product moment correlation coefficient for the population is positive. Right, so we're hypothesis testing here. So obviously we need H0 and H1, right? Whenever we have a hypothesis test. So H0 here is, now don't forget then, when we're working with correlation here, we use the Greek letter rho. So it's kind of like a slanted P, kind of like that. So for H0 then, we say that rho is equal to 0. And then for H1 here, if we're testing for positive correlation, then rho here is greater than 0. And in this case here, we have a one-tailed hypothesis test. Now, what I've got here then is this value of r. So this value of r then is what we call the test statistic. So my test statistic here, which I'll just abbreviate to T.S, is 0.923. So 0.923. And what we do here then is we compare this value here, this test statistic, to a critical value. So my critical value then we obtain from the formula book. Now, I don't know if this will be kind of legible here, if you can read this, but in the bottom left corner here, I've included an excerpt from the formula book, right? And this is what we kind of need to read from here. So we need this table here in your formula book, and it says product moment coefficient at the top right. We've got the levels here. So this corresponds then to the significance level of the test. So 0.10, that's 10%. 0.05 is 5%, 0.025 is 2.5%, 1% and 0.5%. Okay. Now we have a 1% significance level here. So because it's one-tailed, we're in this column here, as opposed to this column here. If it was two-tailed, you half that. So I would then be in this column here, but it's one-tailed, so we don't need to worry about that. I'm just in this column here. And my sample size here then is 10, right? We have a random sample of 10 athletes. So we're in this row here. And basically, I just keep going down then in this column and go across in this row until they intersect. And whatever that value is here, which in this case is 0.7155, this here then is our critical value. So my critical value here is 0.7155, like so. And in this case here, what I can say then is 0.923 is greater than 0.7155. And in that case then, what we do here is we reject H0. So therefore, reject H0. We reject H0 here. And what we say then is there is evidence that the PMCC, in this case here for the population, is positive. Okay, so reject H0. There is evidence. So there is evidence. There is evidence that the PMCC, for the population, is positive. Okay. And there we have it then. So you do need to give a conclusion here. So you need to reject H0 and then kind of state the conclusion in the context of the question, but it doesn't need to be a novel, right? Don't do massive paragraphs, you know, just a couple of lines or a few lines here is absolutely fine. Okay. And then for the very last part here, part E, we don't have much room, but I'll try and just kind of box this off here and answer part E down here. So for part E then, it just says then, explain what your test in part D suggests about the elite female sprinters. So if we have positive correlation here for the population, then what that would suggest here is that on average, elite female sprinters with a greater stride length have a faster sprint speed, right? That's the whole point of positive correlation in the context of the situation here. So let's just try and summarize this here. So this suggests then that this is not going to look pretty. Let me try and redo this here. So this suggests, again, I'll just do it underneath here. So this suggests then that on average, elite female sprinters don't have much room here. This is not the neatest, but hopefully you can just read this. Elite female sprinters with a greater stride length have a faster sprint speed. Okay, and there we have it then. So they have a faster sprint speed. Perfect. Good stuff. So there we have it then. That's the solution to part E. This was the solution here to part D. This was part C, part B, and then part A there. So hopefully, for the first question anyway, quite a nice, straightforward, standard stats question there. Okay, so there we have it then. That gives us the solution to question 1. So moving on to the next question here then, let's just have a go at question 2. So for question 2 then we have Lydia, who is planting a number of seeds. Now, each time she plants a seed, there is a chance that the seed will successfully grow into a healthy plant. And the probability then that a seed grows successfully is 0.52. So on a randomly selected day then, so one day, Lydia decides to plant 20 seeds. And then we want to find the following probabilities here. So for A part 1 then. So to get us started here, the first thing that we should do then is choose a random variable and a distribution to model this situation here. So typically we choose X as our random variable. You could just choose Y or Z, for example. It really doesn't matter. But like I said then, we do normally just choose X here as our random variable. So X here will follow. So what distribution can we use here then to model this situation and this context here? Well, in the context of this situation here, we have a fixed number of trials, right? We've got 20 seeds. I've got a probability of success. So that would indicate here then that a binomial distribution will be appropriate to model this situation here. So X follows a binomial distribution. So N here is my sample size, which in this case here is 20. And our probability of success here, as it's given then, is 0.52. Perfect. So we've got our distribution here and our random variable. Now for the first part then, so A part 1, we want the probability that exactly 6 seeds grow. So what we're looking for here then is the probability that our random variable X here is equal to 6, right? So for a probability such as this one here, the expectation is that you just simply use your calculator, right? They don't really expect you to do this by hand. The expectation, like I just said then, is just use your calculator. So I'll grab my calculator here. So the first thing that we do here then is go into stats mode. I then want distribution. So I'll make a note here then of the options that I choose. So distribution, obviously we're working with a binomial distribution. So I choose binomial. So binomial. And then I get an option here, or one of 3 options here. So it's either going to be BPD, BCD, or inverse B. Now for A part 1 then, because we're looking for the probability that exactly 6 seeds grow here, that tells us then that in this case here, this is BPD. Okay, so BPD. And at this point here, it asks for a few different things. So the data type here, in this case, is a variable, right? It's not a list, it's just a variable. Now for x then, that's this number here. So x is 6. My number of trials, that's n here, is 20. And p then, my probability of success, as it's given here, is 0.52. We input those and we press enter. And what I get here then is the respective probability here. So what I get then, if you've done this correctly, hopefully anyway, is 0.0264 there, 23 significant figures. Okay. So hopefully, nice and easy there then for A part 1, right? The first 2 marks in the bag. Now for A part 2 then, so for part 2 here, what we're looking for then is the probability that at least 9 C's grow. So again, what I want to do here is take this sentence and convert it into, a respective probability. So what I'm looking for here then is the probability that, again, our random variable x here, in this case, right, if we want at least, that is x, is greater than or equal to this number here, 9. Now for this probability here then, I can't just input this as it is into my calculator. So what I want then is 1 minus then the probability of everything below this. So 1 minus the probability that x is less than or equal to 8, right? That's what we're looking for here. So again, I go into stats mode, distribution, binomial again. So still working with a binomial distribution here, but just be slightly careful at this point, right? It's not BPD in this case because we now have a cumulative probability. So now, because at least 9 C's growing, this is BCD. Okay, so BCD. So X then, that's this number here. So X is 8. The number of trials doesn't change, it's just 20. And again, P here does not change. So P is 0.52. We press enter. And what I get here then is 0.197650022. So what I need to do here then is 1 minus that. Okay, so 1 minus 0.197650022. Put this into your calculator here. And again, just round it to say 3 significant figures. And if you do this correctly, then what you should get here is 0.802 there. Perfect. Okay. So that's the solution to part A then. So what about part B here? Well, we're getting a little bit more information here. So in the following summer, Lydia decides to plant 250 seeds. So it tells us here then that she decides to use a normal distribution to estimate the probability that at least 140 seeds will grow successfully. So for B then, we've got again 2 parts here. So for B part 1, what we want to do here then is find the mean and variance of this normal distribution, right? This is our normal approximation here by using a binomial distribution. So don't forget then that mu here is equal to NP. So normally we require then 2 conditions here, that N is large, which in this case it is, right? Because N is 250, and P then is close to 0.5, which in this case here is 0.52. It's close, right? So that's absolutely fine, right? Now it doesn't ask for that, but just be aware that it might sometimes ask you for those conditions, and that's all you'd simply put there. So mu is equal to NP. So mu then is 250 times by 0.52. Input that into your calculator. And what you get here then is 130. So that's mu. What we also want here then is the variance. So sigma squared then is, so what I get here then is NP times by 1 minus P, right? Now, sometimes you might see this as given, sometimes see this given as NPQ, where Q is 1 minus P. They are just the same thing, just so you're aware. I prefer to write it as NP times 1 minus P. So in that case, then, what I get here is 250 times 0.52 times 0.48, which is just the same then as 130 times 0.48. Again, just input this into your calculator, and if you do this correctly, then what we should find here is we get 62.4. Okay, so at this point here, B part 1 is technically complete, but what I'm going to do here then is just define a new random variable and distribution. So what I've got here then is I'll choose a different letter to part A. So I'm going to choose Y here, right? Just going alphabetically. So Y, in this case here, we've approximated a normal distribution. So Y follows a normal distribution where mu is 130, and our variance here is 62.4. Bosh, good stuff. So there we have it then. That is B part 1. And now for B part 2 here, let's just do this underneath them. It asks us to estimate the probability that at least 140 seeds will grow successfully. So what I'm looking for here then is the probability that y is greater than 140, but we need to be very, very careful here, right? When you approximate a normal distribution from a binomial distribution, don't forget that we need to apply a continuity correction, right? So we need to apply, let's just make a note here. So we need to apply a continuity correction, which I'll just shorten to CC here. So CC is a continuity correction. So what I'm looking for here then is the probability that y is greater than 140. Now, if I want the probability that y is strictly greater than 140, what I need to do then is actually find the probability that y is strictly greater than 139.5. Okay, because I need to subtract 0.5 here from 105, because we also need to include the 140 here. Okay. So, sorry, this must be greater than or equal. There we go, that makes more sense. Because I want to include the 140 here, right? Because it's at least 140 seeds, so we need to subtract 0.5 here to get 139.5. I was going to say something doesn't look quite right there. So yeah, the probability that y is greater than or equal to 140 because it's at least 140 seeds will grow successfully. So again, at this point here, you're not expected to do this by hand, just use a calculator. So again, I go into stats mode. Now, just be slightly careful here, right? Because we are now working with a normal distribution as opposed to a binomial distribution. So distribution, and again, I'll make a note here. So distribution, we want the normal distribution, so normal distribution. And in this case here, we work with NCD for the normal distribution as opposed to NPD, just so you're aware here. So NCD, okay? Again, the data type here is a variable. Now just be careful then. So it asks for a lower and an upper here. And this is where students can make mistakes with the normal distribution and working out probabilities for the normal distribution using your calculator. Now, because I'm looking for the probability that y is strictly greater than 139.5, because this is greater than, we put the 139.5, this number here, as the lower value. Okay, so my lower here, so let's make a note then. So lower here, it's 139.5. My upper value then, so for the upper value here, we just choose an arbitrarily large value, right? It really doesn't matter what it is. So all I do then is I just put a load of 9s in. So something like this is absolutely fine. Obviously, sigma here, now again, just be very, very careful. Very easy to make a mistake. So sigma is the square root then of 62.4, right? This is the variance. We want the standard deviation. Square root of 62.4. And then mu here, I don't have much room, but I'll try and fit it on. So mu is, that is this value here, right? So 105, we don't need to do anything with that. Input those and press enter, and then question complete. So what I've got here then is the probability that y, that's this random variable here, is strictly greater than 139.5. By using our calculator here then, what we obtain is 0.115 there to 3 significant figures. Okay, and there we have it then. So that gives us the solution here to question 2. So for the next question here, question 3, as we can see then, there is a lot of waffle for this question, right? It's quite a long question, but let's just break it down step by step, and you should find that this question isn't too bad. Right, so what have we got here then? We've got Tom and Andy, and they're studying the pattern of rainfall where they live in Heathrow, right? Straight away, a little bit scary. The fact that it says Heathrow, that would suggest to me that at some point in this question, the large data set will appear. Always scary. Bound to ruin your day, but don't let it get you down too much. I try not to anyway. So Tom decides to record whether or not it's raining at 8 AM for the next 14 days. So Tom and Andy don't have much better to do, but we'll answer the question for them anyway. So for part A then, it says state the name of the sampling method used by Tom. Just 1 mark for this, should hopefully be nice and straightforward. So the sampling method here is just opportunity or convenience sampling, whichever you prefer to call it. They are just the same thing, and you don't have to give both of these, but I'll just write them both down just so you can see the full solution here. So opportunity or convenience, whichever you prefer to call it. Convenience sampling. And there we have it. Nice and easy there. Okay, so that gives us the solution there then to part A. Now for the next part of the question, we're told that Tom believes that a binomial distribution with n equals 14 would be a good model for the number of days in a 14-day period when it's raining at 8 AM. So for part B then, it just says here then, explain why the binomial distribution may not be a good model in this situation. Again, just 1 mark for this, right? So why might the binomial distribution not be appropriate here? Well, if we're looking at rainfall, right? Rainfall on consecutive days potentially might not be independent. And if they're not independent, then the binomial distribution isn't appropriate, right? Or it won't make a good model in this situation. So we'll just make a note of that here then. So rainfall on consecutive days may not be independent. And there we have it. And we don't need to go into, any more detail on that. Independent. That's absolutely fine there, right? It's just 1 mark. Just 1 simple line is absolutely fine there. Now for the next part of this question here, then we're told that Andy decides to use data from the large data set for Heathrow in 2015. He randomly selects 28 days from the large data set for Heathrow in 2015, and for each day records a daily total rainfall X here, which is given in millimeters. So for part C then, let's just write this down here. It just says using your knowledge of the large data set, and then as we can see here, we've got these 3 bullet points. So for the first bullet point here, it just says, I can't speak anymore. Say what TR means. So TR here would be trace, but I'll write that down in a minute. For the second bullet point then, it says suggest what Andy can do with these TR entries, the trace entries to clean the data set. And then for the third bullet point here, explain what effect this action is likely to have on an estimate of the mean daily total rainfall. Just 3 marks for this, so we get a mark here for each respective bullet point. So for the first bullet point here then, as we just said, right, TR here just means trace. So that's trace there for the first bullet point. And what I'll do here is I'll give the answer to part C as 3 respective bullet points, right, to the 3 bullet points given here. So trace for the first bullet point. And for the second bullet point here, suggest what Andy can do with these trace entries to clean the data set. So what Andy can do here then is just make them 0. So make them 0. So make them 0. And then for the final bullet point here, explain what effect this action is likely to have on an estimate of the mean daily total rainfall. Well, trace values can be between 0 and 0.05 millimeters. So if we just make all of those trace values 0, then this is likely to underestimate the mean value, right? So this will underestimate. So underestimate the mean value as trace values are between 0 and 0.05 there. Okay. And there we have it then. So that's all we need there for part C, right? Just, 3 bullet points just to answer the 3 bullet points given here. Now for the next part of this question here, then part D, this is where we actually have to start doing some maths, right? So what I've got here then is Andy, and he summarizes data in the grouped frequency table shown here. So for part D then, we want to use this information here to estimate the mean daily total rainfall for these 28 days. Right, so I said we need to actually start doing some maths here, but to be honest, this part of the question here, part D, would be something that could just appear on a GCSE maths exam. So really, there shouldn't really be any issues with this. So how would I do this then? Just a quick recap here. So I'd find the midpoints here for x, right? So we can't find a midpoint for that, right? It's just 0. That'd be 0.5, that would be 2, that would be 5, and this here would be 11, right? So that gives me the midpoints. We times that by the frequency, and then we divide by the total of the frequencies, right? We're going to add all of those up and divide by the total frequency. So x bar here is equal to, what I'll do here then is I'll do each product in a bracket just so you can see how I split it up separately, if that makes sense. So I've got 0 times 5. Now, clearly, I don't need to actually write that down, but just for the sake of completeness here, I will do. So 0 times by 5. I've got 0.5 times by 9. So plus 0.5 times by 9. I've got 2 times by 4. So 2 times 4. I've got 5 times 6. And then finally here, we have 11 times by 4. So 11 times by 4. And all we need to do here then is put this over the total of frequencies here, which in this case must just be 28, right? We've got 28 days, so we divide by 28. Good stuff. Just put all of this here then into your calculator, and if you do this correctly then, we should find here 2 free significant figures is we get 3.09, right? And if we just quickly look at the table here, 3.09, that seems pretty sensible, so that's fine there. So 3.09 there, 2 free significant figures. Now, just a quick point here. You could have just done that in your calculator, and that's absolutely fine. But just so you can see the full work in there, that's how we would have done it by hand. Now, for part E then, it says, show that the estimated value of S, subscript double X here, so this is one of our summary statistics here, that the total daily rainfall for these 30 days is 385.0 to 1 decimal place. Right, so how do we answer this here? So for this here then, so S, X, X, don't forget this here is actually given in your formula book, right? And as it's given in the formula book here, it's sigma x squared minus them sigma x all squared. So sigma x all squared all over n. Okay. So let's work out sigma x squared here to begin with. So sigma x squared here, basically we just repeat this process here, but now we just times the midpoints by themselves, right? We just square them, I should say. So again, I'd get 0 squared times by 5, but obviously that would just give me 0. So I won't bother writing it down this time. I then get 0.5 squared times by 9. So 0.5 squared times by 9. I've got 2 squared times by 4. So 2 squared times by 4. I get 5 squared times by 6. So 5 squared times by 6. And then finally here, 11 squared times by 4. So plus 11 squared times by 4. Okay. So just put this here then into your calculator. And if you do this correctly then, we should get here is 652.25 there. Okay, so 652.25 there. So using this formula here then, let's just write this down. So S, X, X here is equal to sigma x squared, which is 652.25. So 652.25 minus them. So what is sigma x here? So sigma x is our numerator here. Okay, so this is sigma x here. So again, just put this into your calculator. And if you do that correctly, we should get here then is 86.5. Okay, 86.5. We square this value here. Then we divide it by n. So n here doesn't change, right? It's just 28 again. Like so. And at this point here, just put all of this then into your calculator. And if you do this correctly, what you'll find then is the value with 1 decimal place is 385.0. Good stuff. So 385.0 there to 1 decimal place. Perfect. Okay. And then finally, for the very last part of this question here, part F, as you can see on the screen here, I've cleared the working from part A, part B, and part C, because we don't need those to answer part F here, but we do really need the working from part D and part E. So I've just kind of shifted those up, and it should give us enough room here to answer part F. Okay? Right, so for part F then, what have we got here? And just a quick note here as well, I did forget to put the marks here for part E, so part E is worth 3 marks, right? So apologies for that. I'll add it to the actual paper. So that'll be fine on the website, but just so you know here, I've added that after moving everything up. Just a quick note there, but don't really matter too much. Anyway, part F. What we're told here is Andy defines an outlier as a value which is more than 3 standard deviations away from the mean. So for part F, it just says state, given a clear reason, whether there could be any possible outliers in Tom's data. Right, so to begin with here, let's actually just work out the standard deviation. So sigma here, so sigma is equal to, again, this is given in your formula, right? So this is the square root then of, and the structure of the question is done for this reason, because sigma here is equal to S x x over n. Okay, now we just work this out here, right? So in that case, then my standard deviation here is the square root of, so it's 385.0, so just 385, right? All over n, where n is 28. Put this here then into your calculator, and if you do this correctly, what you should find here is we get 3.71 there. Okay. So what I now need to do here is work out the 2 limits, right? I've got the lower limit, which is 3 standard deviations away from the mean, and also the upper limit, which again is 3 standard deviations away from the mean. So we've got x bar here minus 3 lots of the standard deviation. This here is my lower limit. So just use your calculator, right? So it's going to be x bar here, which is, well, that is 3.09. So it's going to be 3.09 minus 3 lots of this. Again, just put this into your calculator, right? And if you do this correctly, what you should get here is minus 8.04. And now for the upper limit here then, we get x bar plus 3 sigma here. Okay, I know I said mu there. So x bar plus 3 sigma. Again, I get 3.09. And now rather than subtracting, we just add this on, right? So 3 lots of 3.71. Again, just use the calculator here. And if you do this correctly, what we should get here is 14.22. Okay? So what we're saying here then is any values that are less than minus 8.04 or smaller than minus 8.04, they would be an outlier. And the same here is true, but now greater than. So any values greater than 14.22 would be an outlier. Now, if we look at the frequency table here, and this is for x, by the way, right? Now, clearly, we can't have a value smaller than 0. So for the lower limit here, we don't need to worry about that. You can just basically just ignore that. However, for the upper limit here, well, 14.22 does fall within this class boundary here, right? There could be any value between, well, greater than 14.22 up to 15. And those values would be an outlier, right? So what we say here then is we have possible outliers. So we have possible outliers. Possible outliers in the, what class was it? 7 to 15. In the 7 to 15 group. Okay, and there we have it then. So hopefully part F seems quite intuitive. Don't forget as well, this result here is given in your file book. So not something that you do need to worry about memorizing, but I don't think it's too challenging to kind of memorize here. But anyway, I'm kind of just yapping. So there we have it then. That gives us the solution here to question 3. Now for the next question here, question 4, what I've managed to do then is incorporate one of the pure topics that was missing from paper 2 that we probably would have expected in paper 2 and applied that to the stats part of this applied paper, right? So what have we got here then for question 4? Well, we're told that the discrete random variable z has 5 outcomes, right? And that is when n is equal to 1, 2, 3, 4, or 5. And these outcomes have probabilities given by the nth term of a geometric sequence with common ratio 0.5. And then what I'm given here is the first probability of our probability distribution, right, of z. So for part A then, it just says here, find the complete probability distribution of z, given your probabilities as multiples of p here. Right, so where do we begin here? Now, what I've got here then is the first probability, right? That's p. And if these outcomes have probabilities given by the nth term of a geometric sequence with common ratio 0.5, so r here is 1 over 2, then I'm hoping here it's obvious that the next probability then must be p over 2, right? It's just p times by a half, our common ratio. So I've got p, then got p over 2. So for the next one here, that must be p over 4, right? It's just p over 2 times by a half. We get p over 4. Again, hopefully obvious here, we then get p over 8. And then finally, when n equals 5 here, we get p over 16 here. Okay, so my complete probability distribution of z here would be as follows. So we've got little z here. Underneath them, we have the probabilities, right? So the probability then, z is equal to little z. And then obviously in the top row here is 1, 2, 3, 4, and 5. By the way, it might not be the prettiest. I'm just doing this, freehand. Obviously, in an exam, make it look a little bit neater. It don't have to be amazing, but maybe a little neater than mine. Anyway, so the first probability here, right, that's simply p. You then get p over 2, p over 4, so on and so on. So hopefully nice and straightforward there. So p over 2, p over 4, p over 8, and then finally p over 16 there. Perfect. So there we have it then. That gives the solution here to part A. Now for part B then, it just says show that p is equal to 16 over 31. So how do we show that? Well, what I'm going to do here is use the fact then that the summation here of our probabilities must be equal to 1, right? So sigma of our probabilities here is equal to 1. Okay, so in that case, then what I get here is p plus p over 2. So plus p over 2 plus p over 4 plus p over 8 plus p over 16. This summation here then is equal to 1. Okay, to make life easier here, what I would do then is factor out the p to get p times by, so I've got 1 plus a half plus 1 over 4, 1 over 8, and then finally 1 over 16. And again, all of this here is equal to 1. Put the bracket here then into your calculator. So 1 plus a half plus a quarter plus an eighth plus 1/16. What I should find then is I get p times by 31 over 16. So 31 over 16 p here is equal to 1. And then finally, right, if we just want p here, just divide by the coefficient, which in this case is 31 over 16. So therefore, p is equal to 1 all over 31 over 16, which is equal to 16 over 31 as required, right? So as required there. Perfect. Okay. So that gives the solution there to part B. And then finally, to finish with here, we have the very last part, right? Part C. We want to find this probability here. So the probability then at 2z minus 4 is strictly greater than 3. Okay? So what I do here then is just simplify the inside of the bracket here, right? In other words, just solve for z. So this is equal to the probability then that 2z is strictly greater than 7. So 3 plus 4 is 7. And in that case, then this is equal to the probability that z is strictly greater than 7 over 2, or 3.5, right? So based on our probability distribution here, this probability here, the probability that z is strictly greater than 7 over 2, that would be the probability that z is equal to 4 plus the probability that z is equal to 5, right? They're the only two values that we can take then that's strictly greater than 3.5. That's this value here and its respective probability, and also this value here, and again, its respective probability. So it's p over 8 plus p over 16, but we know the value of p, right? It's p over 8 plus p over 16. If I get this here then over a common denominator, I times this fraction by 2. So that's 2p over 16 plus p over 16. That gives me 3p over 16, right? So 3 over 16 times by 16 over 31. That just gives me 3 over 31 there. Okay. And there we have it then. So that is the solution to part C. This here was to show that for part B, and this here then was the solution to part A. And that gives us the solution then to question 4. Now moving on to the next question here, question 5, as we can see then quite appropriately, right? Just 5 marks for question 5. So quite a small question here in comparison to some of the other questions here then within section A. But let's just work through it anyway. So what I've got here then is the heights of males from a country, and they're normally distributed with a standard deviation of 8.4 centimeters. We then have a statistician who believes that the mean height of males from this country is less than 172.5 centimeters. The statistician takes a random sample of 40 males from this country and finds the mean of their sample to be 170.2 centimeters. So the question then asks us to perform a suitable test using a 5% level of significance to assess the statistician's claim. And as it says here, you should state your hypotheses clearly. So I am hoping that this is quite obvious, right? This question is just based around hypothesis testing. I don't really know how we can make that much more obvious, right? It says state your hypotheses clearly, 5% level of significance. And you should recognize then that we're testing here for the mean of a normal distribution, okay? So, as always with any hypothesis test here, a good starting point is to define our hypotheses then. So we have H0 and H1. So we've got H0 here and also H1, right? So like we just said then, what we're doing here is testing for the mean of a normal distribution. And the mean then of a normal distribution here, that parameter is the Greek letter mu. So I've got mu here then for both H0 and H1. And what we're actually testing here, so what we're testing here then is the statistician's claim, right? That the mean height of males from this country is less than 172.5 centimeters. So for H0 then, we set mu here equal to this value. So mu is equal to 172.5. And then for H1 here, we set mu less than, right? As we're told here in the question. Obviously, this depends on the context of the question. If we were testing whether it's greater than 172.5, then mu would be greater than. Obviously, just read the question carefully in your exam. So mu then is less than 172.5. Perfect. So that gives us our hypotheses here. Now, what we should do here then is define a random variable, okay? So what I've got here then is x. So I choose x here to be the height then of the males from this sample. What I want here is x bar, okay? So we want x bar here. Now, x bar, again, will be normally distributed. So x bar is normally distributed here. So what is our mean? Well, our mean here for x bar is this value of mu. So it's whatever you've got here for H0 and H1. So 172.5. Now, just be slightly careful here for the variance. So for the variance here, I'm going to put this in brackets then. What I get here is this value for the standard deviation, 8.4. But what we need to do here is divide this by the square root then of our sample size, which in this case here, right, is just 4. We've got a sample of 40 males. I've got 8.4 over the square root of 40 here. Now, this is the variance, right? So we need to square this. And there we have it then. So this is x bar here, which is normally distributed with the following parameters. Now, what do we actually want to test here? So what I want to test here is, let's just do that underneath here, the probability then that x bar here, this random variable, so the probability that x bar here is, now in terms of the inequality here, nice and straightforward for a one-tailed test such as this one here. It just follows whatever our inequality is in H1, right? So because mu here is less than 172.5, the same applies here then to our probability here. So this is the probability then that x bar here is less than this value here. So whatever it is found then to be in the sample, right? This evidence here. So 170.2. Like so. So for this probability here then, nice and straightforward, right? Just use a calculator. So let's walk through this together. So we're going to stats mode. I'll do it underneath here. So distribution. So distribution, I press that. Obviously I get all the different distributions here, but clearly we're working with a normal distribution. So I press norm. I then want NCD here. Okay. Just a cumulative probability, right? So NCD. Now the data type here, clearly that's a variable. For the lower and upper then, obviously this depends here on whatever we've got as our probability. So let's just do this underneath them. So lower and upper here. Now I always find this to be a little bit counterintuitive. So if we're testing here for the probability that x bar is less than 170.2, I put this value here, 170.2, as the upper value. Okay, so my upper value here is 170.2, and then my lower value here is an arbitrarily small value. I just put minus and then a load of nines, but anything that's arbitrarily small here is absolutely fine. Okay, something like that. It doesn't need to be too excessive, but you get the idea. Then for sigma and mu here, so sigma and mu here, they're just given then as these two parameters here. So just be very, very careful, right? Sigma is the square root of this. This is the variance. This is sigma squared. So just be very, very careful for that. Easy to make a mistake there. So that is 8.4. So 8.4 over the square root of 40. And then for mu here, well, that's just this value here, 172.5. Apologies, they're not quite aligned perfectly, but you get the idea. Just press enter then. So obviously input that, press enter. And what we get here then is this probability. So what we should get here then is, I'll give this to three significant figures here. I get 0.0417. Okay, that's 3 significant figures. And what I do here then is I compare this to our significance level here, which is 5%. Okay, now it's a one-tailed test, so we don't need to worry about halving this or anything like that. So if we do it underneath here, 0.0417, well, that's clearly less than 0.05, right? So that's less than 0.05 here. And in that case, because our test statistic here, right, this value is just our test statistic, this is less than the significance level here, then what we do then is we reject H0, okay? So therefore, reject H0 here. Reject H0. What we say then is there is evidence. So there is evidence to suggest that the mean height of males from this country is less than 172.5, right? Perfect. 172.5 centimeters there. Perfect. So now it is important here that you do give a conclusion, right? We don't just say reject H0, question done. I mean, it would be nice, but we need to be a little bit more sophisticated than that. We do want to give a conclusion here. So reject H0. And then what we're saying here is there is evidence to suggest that the mean height of males from this country is less than 172.5. And that should make sense then based on H0 and H1, right? H1 here is that mu is less than 172.5. So if we reject H0, then we're saying that H1 basically is true, okay? But there we have it then. So that gives us the solution here to question 5. And then finally, to finish with here, we have the very last question of section A. So we're not quite finished with the paper, right? But we're pretty much finished with the first part of the paper, section A, okay? So for question 6 here, we're given the events A and B which satisfy the following probabilities. And then for the first part of this question, part A, we want to show that 4x plus 5y is equal to 3. So for part A then, where do we begin here? Because we're not really given kind of any clues as to where to start, right? We're just given these probabilities here, and then we want to show this equation here. So to get us started here, I'm going to start with this conditional probability here. So the probability then of B given A is equal to the probability of B intersection A all over the probability of A, right? Like so. Now, we know this probability here is 0.2. So what I've got then is 0.2 is equal to the probability of B intersection A. We don't know what that is, right? So the probability of B intersection A all over the probability of A, which is X. Like so. And in that case then, what we get here is that 0.2x is equal to the probability then of B intersection A. Okay. So obviously we're not quite done here. We're nowhere near this result yet. But what I can also do here is use the fact then that the probability, so make a note here. So the probability then of A union B is equal to the probability of A plus the probability of B minus then the probability of A intersection B. Okay? So the probability of A union B is 0.6. So we've got 0.6 is equal to the probability of A, which is X, plus the probability of B, which is Y. So we've got X plus Y minus then the probability of A intersection B, which is just simply what we just found here, right? I know we wrote that as probability of B intersection A, but they're just the same thing. So I've got X plus Y minus then 0.2x here. Okay? So let's just simplify this here then. So I've got 0.6 is equal to, so x minus 0.2x is 0.8x. So 0.8x plus y. And what we want here then is 4x plus 5y is equal to 3. So if I just times through here then by 5, right, we obtain this result here. So times through by 5. Obviously do the same here on both sides of this equation. So 0.6 times by 5 is 3. 0.8x times by 5 is 4x. And then y times by 5 is 5y, right? And therefore then we obtain 4x plus 5y is equal to 3 as required there. Okay, so there we have it then. That gives us the solution to part A. Now, for the next part of the question, then what we're told here is the events B and C are mutually exclusive such that the probability of B union C is 0.9, and the probability of C is equal to x plus y. So for part B then, let's just do that underneath here. This is split into two different parts, right? We've got B part 1 and B part 2. So for B part 1 then, what we want to do here is find a second equation in terms of x and y. So to do that, we're going to use the fact then that if these two events here, B and C, are mutually exclusive, let's make a note here. So if mutually exclusive, then in that case, the probability of B plus the probability of C is equal to the probability of B union C. Okay. Now we know the probability of B, that's y. I've got y plus the probability of C, which is x plus y. So x plus y there is equal to the probability of B union C, which is 0.9. And if we simplify this here, then we obtain our second equation in terms of x and y. So I get x plus 2y here. So x plus 2y is equal to 0.9. Okay, so that's B part 1. And now for B part 2 then, well, what we've got here is simultaneous equations, right? I've got 4x plus 5y is equal to 3. I've got x plus 2y here is equal to 0.9. So basically, what we want to do here then is just solve these simultaneous equations here. Should be nice and straightforward, just basic GCSE maths simultaneous equations, right? So what I'm going to do here then is just substitute x into equation 1 here. So if I call this equation 1, and this is equation 2. So we just rearrange equation 2, making x a subject here, and then substitute that into equation 1. So what we get here then is the following. So I get 4 lots of, we get 0.9 minus 2y. 0.9 minus 2y plus 5y. So plus 5y is equal to 3. Okay. Let's just expand and simplify here. So 4 times 0.9 is 3.6. 4 times minus 2y is minus 8y plus 5y is equal to 3. So again, let's just simplify here. Minus 8y plus 5y. That gives me minus 3y. So get minus 3y plus 3.6 is equal to 3. If I add 3y to both sides and subtract 3 off both sides, then what I get here is 3y is equal to 0.6. And then finally, right, we just want y here. So we just divide both sides by 3. And therefore, y is equal to 0.2. But be careful, we're not done here. Don't forget, we also need to find the value of x, right? So just use either of these two equations here. So if y is 0.2, x plus 2 lots of 0.2, so 0.4 is equal to 0.9. 0.9 minus 0.4 is 0.5. And therefore then, x is 0.5. Perfect, good stuff. So that gives the solution to part B. And then for the very last part here of this question, part C, I appreciate, by the way, that this is kind of going in a bit of a funny order. So let me just kind of box this off here. So that was part A. That was part B. So to finish with here, I'll just do part C in a different color just so you can see the difference. I'll do it in green. Doesn't really matter too much, but just so I don't cause any confusion. So for part C then it says, showing all your working clearly, determine whether A and B are statistically independent. So given that we have conditional probabilities here, they will be independent if, the probability of B given A is equal to the probability of B, right? Now, the probability of B given A is 0.2. Let's highlight that again. So let me just make a note here. The probability of B given A is 0.2. The probability of B is Y. But we worked out that Y here is also 0.2. So probability of B is 0.2. So in that case then, the probability of B given A is equal to the probability of B, and therefore these two events then, A and B, are statistically independent. So therefore A and B are independent. Okay. And there we have it then. So hopefully, the last part anyway wasn't too bad. Obviously, you can go about that in a different way using intersections as well. There we go. I can't speak. You can do it like that. That's also fine. I just think here, this is the easy way to answer part C. Okay. So there we have it then. That gives us the solution then to the very last question of section A, question 6 here. Now, unfortunately, we do have to move on to the mechanics. If you're like me, you're not much of a fan of mechanics then. It's always a little bit painful, but there we have it, right? So that's the solution to question 6. Let's move on then to section B. So for the next section of this paper here, as we can see on the screen, right, we have section B on mechanics. So we've got question 7 here. What we've got here then is a particle that moves with constant acceleration, 8 meters per second squared, in a straight line from rest to 20 meters per second in 40 seconds. We're then told that the particle decelerates from 20 meters per second to rest with constant deceleration, half a meters per second squared. And then what we want to do here is find the following. So let's just start here then with part A. So clearly, based on the context of this question here, we're working with constant acceleration, right? I'm hoping that's pretty obvious. So we're going to be working with the constant acceleration formulae, or sometimes known, and it's what I know them as, the Suvat equations, okay? So let's just start then by listing the information that we do know here. So what I know here then is we start from rest. So U here is 0. V here, our final velocity, is 20 meters per second. So V is 20. T then is 40 seconds, right? So T is 40. What else do we know here? So the only thing remaining here then is the particle moves with constant acceleration, 8 meters per second squared. So that's what we want to find, right? We want to find the value of A. So I'll put A here with a little question mark, right? Because that's what we want to find. So A with a question mark there. Now, based on what we know here, what constant acceleration formula or what Suvat equation can we use here? So we've got U, we've got V, we've got T, and we want to find A. So in that case, then what we're going to use here is we're going to use V is equal to U plus AT. Okay, so V is 20, and that's equal to U, which is 0. So I won't bother writing that down, but if you want to, you really can. But it's not necessary. And then AT here. So A we don't know, so I'll just write that as A times by T, which is 40. So I get 48 there. So nice and straightforward then, right? We just want the value of A here. So just divide both sides by 40. And in that case here, A is 20 over 40, or just a half there. Okay. So hopefully nice and straightforward there anyway for part A. So A is equal to a half. Now for the next part of this question here, then part B, a little bit more challenging, but again, this is the first question for the mechanics part, so we shouldn't be really expecting anything too challenging here, right? Now for part B, then what we want to find here is the total distance traveled by particle. Now, what we need to do here is think about this in two parts. So we've got the part here where the particle is accelerating, so the distance traveled while the particle is accelerating, and we also have the distance traveled then whilst the particle is decelerating, okay? So let's just start then when the particle is accelerating. So whilst accelerating here, what do we know then? So what we know here is the following. So we know that U is 0. U is 0. V is 20. So V is 20. Again, we know what T is. T is 40. We also know A, but for now, I'm not concerned about that. So T is 40. What we want to know here then is S, right? The displacement here, the distance traveled whilst accelerating. So I've got S here, and and I'll put a question mark next to that, right? Because that's the thing that we want to find. So based on this information here, what Suvat equation or constant acceleration formulae can we use here? So what we're going to use here then is the following. So I'm going to use them. To use S is equal to U plus V all over 2 times by T. Okay. So S, we don't know what that is, right? So I'll just put S there. So S is equal to, so U is 0 plus V, which is 20. So I get 20 over 2 times by T, where T is 40. So 20 over 2 is 10. 10 times 40 gives me 400 there. Okay. So whilst the particle is accelerating here, it travels 400 meters. Okay. We only just need to do the same here, but whilst the particle is decelerating. Okay. So we'll do that over here on the left-hand side. So whilst decelerating here, I don't know if I spelled that right, but it doesn't matter. I'm not an English teacher, so that's fine. That's probably wrong. But anyway, so whilst it's decelerating then, what do we know here? So what I know here then is that it decelerates from 20 meters per second. So U here is 20. So it decelerates from 20 meters per second to rest. So in that case then, V is 0. Our final velocity is 0. What else do we know here? What do we know here? We know that A, so just be slightly careful here, right? Because I don't know how long it decelerates for. So actually, that's the first thing that we need to find here, right? So A is constant deceleration here of a half A. So I'm going to take that as negative, right? So that's minus a half A. But we know then that A here is a half. So minus 1 over 2 times 1 over 2, minus 1 over 4 there. Okay? And to begin with then, the thing that we need to find here is T. How long does it travel for? Okay, so I'll put a question mark there. So based on what I've got here, so U, V, A, we want to find T, what we're going to use here. So what I'm going to use here then is, as we did in part A, right, I'm going to use V here is equal to U plus AT. Okay, so V then is 0. So 0 is equal to U, which is 20, plus AT. So A here is minus 1 over 4 times by T. It's minus 1 over 4 T there. So all we need to do here then is just solve for T, right? So add 1 over 4 T to both sides. So T over 4 is equal to 20 times 3 by 4 then, and T is equal to 80. So what that's telling us here then is the particle decelerates for 80 seconds here. And what I'm going to do now is just repeat this process here because we now know the value of T. So again, whilst decelerating, U here, it's just the same, right? So U is 20. V is 0. So V is 0. T now is 80. What we want to find then is S, right? The displacement. So I've got S here. And again, I'll just put a question mark next to that, right? Because that's the thing that we want to find. And again, we're going to use this here. So use S is equal to U plus V over 2 times by T. And therefore, in that case, then S here is equal to, so U plus V. So that's 20 plus 0. So we're going to get 20 over 2 times by T here, which in this case is 80. So 20 over 2 is 10. 10 times 80 is 800. So whilst the particle is decelerating then, it travels 800 meters. So to finish with here then, the total distance traveled by the particle would be the sum then of the two individual displacements here. So I'll do that in a different color then, just so you can see the solution a little bit easier. So therefore, the total distance traveled is So it would be 800 plus 400, so 1,200 meters there. Okay, and there we have it then. So that gives the solution there to the first question of the mechanics part, or if it's following on in numerical order, question 7 here. Now for the next question here, question 8, what we've got then is a particle P that moves under the action of a single force in such a way that at time t seconds, where t is greater than or equal to 0, its velocity v meters per second is given by the following. We're then told that the mass of the particle P is 0.2 kg, and all we want to do here then is just find the time at which the magnitude of the force acting on the particle P is 3 newtons. So to get us started here then, let's just recall Newton's second law here. So F is equal to ma, right? This is just Newton's second law here. Now, the issue here then is we've got the velocity vector, but clearly we need then the acceleration vector here. So if I just make a note then, so SVA here. So we've got the velocity vector here, but we want the acceleration vector. So we need to move down the list here. And don't forget then, to move down here, we differentiate with respect to time t. So d by dt here. It's not really appropriate for this question. It doesn't really apply, but just as a quick point of revision here, if you're going the other way then, so for example, you've got the acceleration vector and you want the velocity vector. So we're going backwards then. The way that we do that here is by integrating with respect to time t. So the integral then of dt here. But anyway, that doesn't really apply to this question. But like I said, you do need to know that. But anyway, like we just said then, we've got the velocity vector here. We want the acceleration vector. So all we need to do here then is just differentiate v with respect to time t. So should hopefully be nice and straightforward here. So the acceleration vector here, a, is equal to, so just go term by term here. So the t squared, that differentiates to give us 2t. To get 2t there. The minus 3t, that differentiates to give us minus 3. Like so. That's for the I component there, so 2t minus 3i. Like so. And then for the minus 9tj here, well, nice and straightforward, then that just differentiates to give us minus 9j there. So minus 9j. Okay? If I just make another note here then, let's just rearrange this equation here, making a the subject. So a here, nice and straightforward then, is equal to f over m, right? So what I need to do here is find the acceleration, sorry, not find the acceleration, find the magnitude of the acceleration vector. And then we also need to find here the magnitude of f over m. Now, we know the force here, that's 3 newtons, and we also know the mass of the particle, right? That's 0.2 kg. So that should be nice and straightforward. So for the magnitude then of the acceleration vector here, what do we get here then? So nice and straightforward, then we simply get 2t minus 3 squared. So 2t minus 3 squared plus minus 9 squared. So plus minus 9 squared there. So just expand here these double brackets. So I get 2t times 2t, so that's 4t squared. Well, what else have I got here? Sorry. So I've got 2t times minus 3, so that's minus 6t. But again, we repeat that. So 2 lots of minus 6t, we get minus 12t. And then finally here, minus 3 times minus 3 is plus 9. We've also got minus 9 squared, so that is 81 there. So plus 81. So let's just simplify this here. So what do we get then? 4t squared, can't do anything with that. Can't do anything with the minus 12t here. Like so. But obviously 9 plus 81, that just gives us 90 there. Okay. So that's the magnitude then of the acceleration vector here. Now for the magnitude then of f over m here, let's just do that underneath. So for f over m, what do we get here? So f here is 3 and m is 0.2. So this would simply be 3 over 1/5 all squared, right? So hopefully nice and straightforward there. So 3 divided by 1/5 here, that's just the same as 3 times 5, so that's 15. 15 squared is 225. Okay. So what I'm doing here is setting these equal. So the magnitude of the acceleration vector here is equal to the magnitude then of f over m. So if we do that, what we get here then is 4t squared minus 12t plus 90 is equal to 225, right? So what I've got here is a quadratic equation, which we want to solve for t, right? So to do that, let's just make one side of this equation equal to 0. So let's just subtract then 225 off both sides. So I get 4t squared. So 4t squared minus 12t, and then 90 minus 225, that gives me minus 135 there. And this here then is equal to 0. Now, like we just said then, we want to solve this quadratic equation here for t. Obviously, just put this into your calculator, right? Don't need to be anything too fancy. So if you put this into your calculator here then, what you should get is, so obviously this would factorize here. I get 2t minus 15 times by 2t plus 9. Okay, and this here then is equal to 0. So this will give me two solutions here, right? I would get them, so I'd get 2t is equal to 15, right? Because 2t minus 15 is equal to 0. Add 15 to both sides, and then divide through by 2. So t here is equal to 15 over 2, right? Or 7.5. What I've also got here is this solution. So 2t plus 9 is equal to 0. Subtract 9 off both sides. So 2t is equal to minus 9. Then divide both sides by 2. And in that case, we obtain that t is equal to minus 9 over 2. But clearly, we're going to omit this solution here because t is greater than or equal to 0, right? T just represents time, t seconds, so clearly it can't be negative. So you just omit that solution there, and therefore then t is equal to 15 over 2. So the time at which the magnitude of the force acting on P is 3 newtons is when t is equal to 15 over 2 there, okay? And there we have it then. So, hopefully not too challenging there, but there we have it then. So that gives the solution there to question 8. All right, so for the next question here, question 9, as we can see then, as with most mechanics questions, right, we've got a particle. So the particle has a mass of m kilograms, and it's sliding down a rough plane that's angled at theta to the horizontal. The coefficient of friction between the particle and the plane is mu. And all we want to do here then is just show that the acceleration of the particle is independent of its mass. So where do we begin here? Well, obviously what we've got here then is an inclined plane, right? What I would always recommend doing, especially if you don't have a diagram like this, right, is just draw a quick diagram. It doesn't need to be perfect, just so we can visualize the forces here and see what's actually going on. So I'll draw the horizontal, something like that. And I've got my inclined plane here. Again, something like that. The angle of inclination here is given as theta. So that's theta there. At some point on the plane, I've got my particle. I'll just draw that like that, right? Doesn't need to be perfect. And what I also need here then is the relevant forces, right? So with the particle here and the rough inclined plane here, we have a normal reaction. So we've got our normal reaction here. I'll label that as R. We've got friction. So the coefficient of friction between the particle and the plane is mu. So the particle is sliding down the plane. So friction opposes motion. So friction is acting up the plane, like so. So that would be mu R here, because the coefficient of friction is mu. We've also got the weight here. So the particle has a mass of m kilograms, so the weight then is mg. So mg here, like so. Now, what will happen here is this force will need to be split into components. So, as you can see, that's not perfect, but you get the idea, right? It just forms a right angle triangle here. This angle will be the same as this angle here. So that will also be theta, okay? So this force here then, acting downwards, that would be mg cos theta. So mg cos theta. And then this force here, acting in this direction here, that would be mg sine theta. Okay? And then the only thing that I'm actually missing here is the acceleration, right? So it's accelerating down the plane here, like so. And I think at this point here, that is the relevant forces then for our diagram. And we should have enough now to actually answer this question. Okay. So to get us started here, what I'm going to do then is resolve perpendicular to the plane here. Okay. So resolve perpendicular to the plane, taken up as positive here. So what would we get here then? Now, we would need to use Newton's second law here, right? F equals ma. But in terms of perpendicular direction here, the particle doesn't move, right? There's no motion perpendicular to the plane. So A would be 0. And what that means then is forces acting upwards will be equal to forces acting downwards, right? So acting up then, we've just simply got the normal reaction here, R. So R is equal to, so what the force is acting downwards here, perpendicular to the plane? Well, that would simply be this force here, right? Mg cos theta. So R is equal to mg cos theta. Okay? So we've resolved perpendicular to plane there. We can't do anything else with that. We're now going to resolve parallel to the plane here. Okay, and again, we do need to use F equals ma here. Newton's second law, right? So we now resolve parallel to the plane, taking down the plane as positive here. So what would I get here then? So going down the plane then, well, I've got mg sine theta here. So mg sine theta. There's no more forces acting down the plane here, right? Parallel to the plane anyway, so that's fine. What's going the opposite direction then? So what's going up the plane here, but parallel to the plane? Well, that would be friction, right? Minus mu r here. So minus mu r. And using Newton's second law here then, this will be equal to the mass times the acceleration. Well, the mass is m, and the acceleration here, we just define that as a, right? So what I get here then is ma. Now, I know then that r here is mg cos theta, right? Because we derived this here then by resolving perpendicular to the plane. So we're now going to substitute r here into this equation. So I get mg sine theta minus mu r, so minus mu, times by r here, which is mg cos theta. So I get minus mu mg cos theta, and that is equal to ma. Okay? So what I can do here then is just divide through by m, right? I've got mg sine theta here. I've got this mg here. We've got m times by the acceleration here, right? So at this point here, we can just divide through by m. And in doing so, what I obtain here then is g sine theta. So I get g sine theta minus, so I get minus mu g cos theta here. So minus mu g cos theta is equal to a. Okay? And to make things look a little bit prettier here, what we can do then is factor out g here. So factoring out g here, we get g times by, so I get sine theta, minus then, so what do I get here? So minus mu cos theta, right? So minus mu cos theta is equal to the acceleration a. And that is supposed to be an a. It's come out pretty terribly. Let's try again. English is hard. There we go. Looks a little bit better. So to finish with then, what you should recognize here is that m does not appear in this equation, right? So m, being the mass, does not appear in this equation here for the acceleration. So let's make a note here. So m does not appear. And why is that important then? Well, if m does not appear, what that means here then is the acceleration of the particle is independent of its mass, right? So therefore the acceleration of the particle is independent of its mass. Okay. And there we have it then. So just a quick conclusion there, that m does not appear, and therefore the acceleration of the particle is independent of its mass, right? And there we have it then. So that gives us the solution here to question 9. Now for the next question here, question 10, we have a particle P that is projected from a point on a horizontal plane with speed u at an angle of elevation theta, as we can see here then in figure 1. Now for the first part of this question here, then part A, all we want to do here, when I say all we want to do here, right, as we can see it's 6 marks, so not a particularly small part of the question here, but what we want to do then is show that the range of the particle can be given as follows. Right, so how do we do this here? So starting off with part A then, what we're looking to do here is prove one of the projectile motion formulae, right? And this is for the range here. So to get us started here then, let's just take components of velocity horizontally and vertically, okay? I'll do this here then in a different color just so you can see. So for the horizontal component, something like this here, and this would be u cos theta. So u cos theta there for the horizontal component, and then for the vertical component here, we get something like the following, right? And this is u sine theta. So u sine theta there, okay? So what I'm going to do here then is resolve vertically and horizontally then. That would give us these components here. So I've kind of already done it, but like I said, I'll do it a little bit more formally over here. So resolving horizontally here then, taken to the right as positive. And what I get here is ux is equal to u cos theta. These should be capitals, by the way. I have a bad habit of not doing them as capitals. So u cos theta. There we go. And then resolving vertically here, taking upwards as positive. And what I get here is uy is equal to u sine theta. Okay. So let's just start here then by resolving vertically to find the time of flight, right? We need to start by doing this. So resolving vertically here. So what I'm considering here then is going from this point. I'll do it in a different color. Let's do it in red. So going from this point here, let's call that A, to this point here, let's call that B, right? Resolving vertically here. Now, in terms of the displacement here, in a vertical sense, I'm hoping it's quite obvious that the displacement is just 0, right? We start at this height here, we finish at this height here. There's no change there in the displacement. So, going back to my original pen color here, taking upwards as positive here then. So S is equal to 0. U then, my initial velocity here. So U, don't forget here, this is in the vertical sense. That would be uy here, which is u sine theta. So u sine theta. What else do we have here? We've got acceleration. So A. Now, we have the effects here of gravity, right? So, due to gravity then, well, obviously gravity is acting in this direction here. but we took upwards as positive. So A is equal to minus G. And then what we want here is the time T. Okay, so I'll just put a question mark there. That's what we want to find, right? So what I'm going to do here then is use one of our Suvat equations here, right? So I'm going to use then S is equal to UT plus a half AT squared. Okay, so S is 0. U times T, so that's going to be, so if I just put T as T, right? I get UT sine theta plus a half times by A, which is minus G. So times minus G times T squared there. Okay. So what I can do here then is factor out a T here on the right-hand side. So 0 is equal to, factoring out the T then, so I get T bracket U sine theta minus then a half. So minus a half GT here, right? Because this was T squared. Factor out the T, we still got 1 remaining here. And all we want to do here then is just solve for T, right? So I get one solution here. That's when T is equal to 0, which hopefully is obviously it's this point here, the point A. And then this solution here, this would be for the point B. So U sine theta minus a half GT is equal to 0. Okay. And like we said then, all we want to do here is just solve for T. So add a half GT to both sides here. So half GT is equal to U sine theta. Times through by 2 here. So we get GT is equal to 2U sine theta. And obviously we want to solve for T here. So divide through by G as well. And in that case then, what we get here is that T is equal to 2U sine theta over G, right? So this here then is the time of flight from the point A to the point B here for the particle P. So what I now need to do here is resolve horizontally. I'm going to take to the right as positive here. I'm also going to use the fact here then that S, I'm going to use here, S is equal to VT, right? So what I'm looking to find here is the range of the particle. That's this horizontal distance here. So we just call that R here for the range. So in that case, then R here is equal to, so that's my displacement S here. The range, right, it's just the same thing. So R is equal to V times T. So V here is just my horizontal component. So U cos theta. So U cos theta times by T, where T here is the time of flight that we just deduced previously. So U cos theta times by 2U sine theta over G, right? So let's just multiply together here, see what we get. So I get 2U squared. So 2U squared sine theta cos theta all over G. And what you should recognize here then is, let's do it at the top here, 2 sine theta cos theta is identical to sine 2 theta, right? So in that case, then what I've got here is U squared times by 2 sine theta cos theta, which is just identical to sine 2 theta. So what I've got here then is, it should be a U that. It's not very good. Let's try again. So I'm going to get U squared. Looks a bit better. Sine 2 theta. Sine 2 theta over G as required there. Perfect. Okay. Now, as we can see then, that is the solution to part A. That gets us the 6 marks there. But unfortunately, I took up the full screen just to answer part A. So let me just quickly pause the video, clear the screen, and then we can have a go at answering part B and part C here. So we've now cleared the screen here, so let's just have a go then answering part B and part C here. Now just as a quick point then before we actually have a go at part B and part C, even if you couldn't derive this result here in part A, don't despair. You can still go on to answer part B and part C, right? Because all we need then is this result here, the range. And that's given to us. So that's absolutely fine. You can still use this result here, even if you can't derive it. So for part B then, what do we want to do here? So it says, hence find, as theta varies, the maximum range of the projectile. Now, this here is the range, right? So R is equal to u squared sine 2 theta over g. So R is a maximum when sine 2 theta is equal to 1. So let's make a note here. So R is a maximum. R is a maximum when sine 2 theta is equal to 1. And this is when theta is equal to 45 degrees. Which is when is equal to 45 degrees. Okay? And therefore the maximum range here, so the maximum range here is, like we just said, this is when sine 2 theta is equal to 1. So just simply get u squared over g. So u squared over g there. Okay? And there we have it then. So that gives us the solution to part B. And then finally here for part C, it says, given that the range of the projectile is 3u squared over 4g, find the two possible values of theta, giving your answers to the nearest 0.1 degrees here. So what I've got here then is the range of the particle being equal to this here. So I've got u squared sine 2 theta all over g is equal to 3u squared over 4g. Okay? So this u squared here cancels with this u squared here. What else have we got here? I've got this g. We can cancel that with this g here. So what I get left with here then is sine 2 theta So sine 2 theta is equal to 3 over 4, right? 3 over 4 there. So all I want to do here then is just solve for theta, right? Just a very basic trig equation here. So 2 theta then is equal to sine inverse of 3 over 4, right? We are working in degrees here, as we can see. So just make sure that your calculator is in degrees as opposed to radians. So 2 theta then is equal to, so I get 48.59 degrees here. And obviously we have another solution here of 180 minus this value here. So 180 minus 48.59, that gives me 131.41 degrees. Okay. And clearly we just want theta, right? Obviously give it to the nearest 0.1 degrees. So therefore theta is equal to, so what I get here then is just dividing 3 by 2, right? I get 24.3 degrees and also 65.7 degrees there. Okay. And there we have it then for part C. So that's the solution to part C. This was the solution here to part B. And that gives us the solution then to question 10. Now for question 11 here, what we're told then is at 9 AM, two ships P and Q have the following position vectors here relative to a fixed origin O. Their velocities are given as follows respectively. And then for the first part of the question here, part A, what we want to do here then is write down the position vectors of P and Q after T hours. Right, so let's start with P here. So for part A then, hopefully we'll have enough room. So this is for the position vector then of P here. So what would this be here then? So this would be the initial position plus the velocity times by time t, right? So r p naught plus the velocity of p times by t. Okay. So what does that give me here? So therefore, rp is equal to, so the position vector then for p here, or the initial position vector here, is given as, I should say the initial position anyway, is given as I plus 4j. So that's I plus 4j plus then the velocity for p here, which is this, so I minus 2j. So I minus 2j times by t here. Okay. So let's collect here then the components for I. Well, I say collect the components, the coefficients here. So I've got 1 here plus 1t. So it's just 1 plus t I there. So 1 plus t I there. For j then, I get 4 minus 2t. So plus 4 minus 2t. Okay, so this here then, this is the position vector of p after t hours, right? So that's rp there. Hopefully nice and straightforward. We now just need to repeat this process again then for the position vector of q after t hours. So in that case then what I get here is rq is equal to, so again it's just this process here. It's rq naught plus the velocity of q here times by t. Okay. So therefore then, rq is equal to, so the initial position here then for q is given as 3i minus j. So what we just said then, I get 3i minus j. So 3i minus j plus then the velocity of q times by t here. So the velocity of q is minus I plus 3j. So plus minus I plus 3j. Okay. And again, all we want to do here, oops, I forgot to times by t here. Apologies, like so. And again, all we want to do here, just as we did before, is just collect then the coefficients here for I and j, right? But now doing it for q. So what do we get here? I'm going to get 3 minus 1t, so just 3 minus t, right? So 3 minus t I there. And then doing the same here for j, or the coefficient of j, right? What I'd get here then is minus 1 plus 3t. So plus minus 1 plus 3t. Perfect. Okay. And there we have it then. So hopefully nice and straightforward there. That gives us the solution to part A. Now for part B then, it just says here, show that t hours after 9 a.m. the displacement vector of q relative to p is given by the following. So what I'm looking for here then, for part B, is the position vector then of PQ, right? That's all it's saying here. We want the position vector of PQ, okay? I should write this as a vector here. So this would simply be the position vector of Q. So the position vector of Q minus the position vector of P, okay? I don't think I'll have enough room to do it here, so I'll just do it underneath them. So what would this be here? So the position vector of Q is this here. So what I'm going to get then is, I'll do this in one big bracket here. So I get 3 minus t. That's for I here. So 3 minus ti plus, I then get minus 1 plus 3t j. Okay. And then what we do here is we subtract the position vector of p, right? So minus then, again, let me close this bracket here. I'll do this in a separate bracket then. So minus RP here, that is this result. I get 1 plus t, that's for I there. And then for minus 2t, so for minus 2t there. Okay, we'll close that as well. So grouping here then the coefficients for I and j respectively, what I'd get then is, so what am I going to get here? So for I then, I get 3 minus t minus 1 minus t, right? So just be careful with the signs here. It is, very easy to make a mistake. So like we just said then, I get 3 minus t. So 3 minus t, and then minus 1 minus t. So minus 1 minus t there. And this here then is the coefficient for I, like so. And we're going to just repeat this here then for j. So what would I get here then? So it's plus, so we get minus 1 plus 3t. So minus 1 plus 3t. What else have we got here? So I've got plus 4, but don't forget we're subtracting this. So minus then this plus 4, so minus 4, and then minus 2t. So again, just be careful with the signs, right? So I get minus 4 plus 2t. Okay, and this here then is the coefficient of j. So let's just simplify these two brackets here. 3 minus 1 is 2. I get 2 there. Minus t gives me minus 2t. So you get 2 minus 2t there for I. Perfect. That's what we wanted here, right? So that's looking good. Let's just do the same here now for j. So I've got minus 1, minus 4. That's minus 5, right? So you get minus 5 there. I've also got 3t plus 2t. So I get plus 5t there. And that there is for j, right? So this is minus 5 plus 5t here. So I don't know quite how clear that is. Just redo it. So minus 5, there we go. That looks better. So minus 5 plus 5t there. And that's for j. Perfect, right? That's exactly what we wanted here. So as required there. And there we have it. So as required. Perfect. And then finally, the very last part of this question here, part C, it just says then, show that the two ships collide and deduce what time this occurs. Right, so for part C then, if these two ships then, P and Q, collide, then the vector PQ would be 0, okay? So in that case then, this vector here, what I'm going to do then is take both the coefficients here for I and j, set those both equal to 0 and solve. And what we should find then, if they do collide, is the value of t here is consistent. So in other words, the value of t here should be the same for both of these, right? Once I set both of these equal to 0. If they're not consistent, then they don't collide. But given that the question wants us to show that they do collide, then we should be able to find that they are consistent, right? If we don't, then there's a problem, but it should work out, right? So let's just do that here then. So 2 minus 2t is equal to 0. Add 2t to both sides. So 2t is equal to 2. Divide through by 2, and therefore t is equal to 1. Perfect. And when I just repeat this here then with minus 5 plus 5t, so minus 5 plus 5t is equal to 0. Add 5 to both sides. So 5t is equal to 5. And then just divide through by 5, right? And therefore t, again, is equal to 1. Perfect, right? That's what we wanted here. We should have got the same value for t here for both of these equations. If we didn't, there was a problem. So what that shows here then is the ships collide. And what that's telling us here is they collide 1 hour, where t is in hours here, right? So this is 1 hour after 9 a.m., right? So Therefore, the ships do collide. So the ships collide. So the ships collide. And given that it's after T hours here, where T is 1, the ships collide at 10 a.m. there. Okay. And there we have it then. So hopefully nothing too particularly challenging anyway for that question. But there we have it then. So that gives us the solution here to question 11. And then finally, to finish with here, we now have the very last question, question 12. So what we've got here then is a beam AB of mass 10 kilograms and length 4 meters. And this is smoothly hinged to a vertical wall at one end A. The beam is held in equilibrium in a horizontal position by a rope of length 1 meters. And one end of the rope is fixed to a point D on the wall, which is vertically above A. So again, we can see that here on figure 2. The other end of the rope is fixed to a point C on the beam so that the angle ADC is 30 degrees as displayed in figure 2 above. We're then told that the beam is modelled as a uniform rod and the rope is modelled as a light inextensible string. And it says, using the model, find the following things here. Right, so where do we begin here? Certainly not the easiest question to work through. So starting off with part A then. What we want to do here is, using the model, find the tension in the rope. So to get us started here, let's just add then the relevant forces to our diagram here. So like it says then, there's tension in the rope here. That would be in this direction here, like so. That's my tension there, T. Now, this force here, the tension, we need to split that into components. So I'll do this in different colors. Let's do the vertical component here in light blue. So we get this angle here, which in this case would be the same as this angle here. So that's 30 degrees. I don't have lots of room here, but hopefully you can just about see this. So this angle here is 30 degrees. What else do we have here? Well, the vertical component then would be T cos 30 degrees, right? So T cos 30 degrees. And this component here is in that direction. We also have the horizontal component here then for the tension, right? That's in this direction here, okay? And that would be T sine 30 degrees. So T sine 30 degrees there, okay? We've also got the weight force here acting vertically downwards. We'll do that in dark red here. So because the beam here is modeled as a uniform rod, I know then that the weight here acts vertically downwards in the center of the rod. So if the full rod here is 4 meters, or it has a length of 4 meters, then the weight here is 2 meters across, right? Slap bang in the center. So this distance here then is 2 meters, but we'll come back to that later on. So that's mg there. Am I missing anything here? So I think for now, that's okay. Okay, but we can always revisit this if we are missing anything a little bit later on. So going back to my original pen color here, what do we need to do here then? So what we need to do here is take moments. Now, it's up to you where you take moments about here, but the most obvious choice here to take moments about is A. And the reason for that is because we don't need to consider the forces then from the wall. And in other words, it will just give us an equation in T only. So I'm going to take moments about A here, okay? So taking moments about A here. Now, let's just be careful here as well, because what I also need here is this distance here from A to C. Okay, that is C there underneath. It's kind of cut off a little bit. I need this distance here from A to C, right? Because I've got the force here. So that distance then from A to C, we can easily deduce that by using some basic trigonometry here, right? So the length then of AC here is equal to, so by some basic trigonometries here, I'm going to get, it's going to be AC over 1 is equal to sine 30. Yeah. So AC over 1 is equal to sine of 30 degrees. So therefore, in that case, then the length here, AC, is simply sine 30 times by 1. So I just get sine 30, right? Like so. So now, taking moments about A here, what do we get then? So I've got the vertical force here, T cos 30. So I've got T cos 30 degrees. I then times this by the length here of AC to take us back to A, right? I get T cos 30, or T cos 30 degrees, times sine 30 degrees. And because the rod here is held in equilibrium, then this will be equal to the weight force, right? So this is equal to mg times by 2, right? Because this length here is 2 meters, right? This length here is 2 meters. From here to B is also 2 meters because it's a uniform rod. So I get mg times by 2, okay? And all we need to do here then is just solve for T, right? Just rearranging and solving for T. And that would give us the tension in the rope here. So hopefully nice and straightforward here. T is simply equal to 2 mg all over then sine 30 degrees times cos 30 degrees. So we get sine 30, cos 30. Like so. So M here is 10 because it has a mass of 10 kg here. So I get 2 times 10, so that's 20. I get 20g. So 20g all over sine 30 cos 30. Like so. Just put this here then into your calculator. So as a decimal here, what I get then is 452. 452.642, so on and so on. Now, what I would do here is just round this to 3 significant figures. So what I'll get here then is 453 newtons there. Okay, and that's for the tension in the rope there. Okay. Now, if you want to here, you could give this in exact form. That's also fine, and we will need to use that later on in the question. But for now, I'll just give it as this numerical equivalent here. Okay, so there we have it then. That gives us the solution to part A. Now for part B then, what are we doing here? So we want to find then the direction of the force exerted by the wall on the beam at A. So at A here. So basically what we're saying here is the tension force is pulling towards the wall, but because of that, we will have a force pushing back from the wall. And in this case here, it won't be exactly horizontal, right? It's going to be in some direction, either above or below. We don't obviously know what that is yet, but we're going to find that out a little bit later on. Okay, but that's what we need to find here. So to get us started here, what I'm going to do then is resolve vertically here. Okay, now we need to choose a direction as positive. Typically we just take upwards as positive, right? But you can take downwards as positive, and we might guess incorrectly here, which is fine. Okay, if we guess incorrectly, what will happen then is the force there will be negative, right? And we'll probably see that later on. So let's resolve here vertically, taking upwards as positive. So let me just add some forces here to my diagram again. Let's do this in green here. So I'm presuming here there's some force, right, acting upwards here. I'm going to call this force here acting upwards Y. Okay. And we also have a force acting horizontally here. What color can I use here? Let's do that in purple. We have a force acting vertically here, which I'm going to call X. Okay, so X and Y here are my two new forces then for part B. So resolving vertically here then, what would we get? So I've got this force here, T cos 30 degrees. So T, do it underneath here. So T cos 30 degrees plus this force here, Y, because we're assuming it's acting upwards. That could be wrong, but for now we'll assume it's acting upwards. So T cos 30 degrees plus Y is equal to the weight force here. This force is acting vertically downwards, right? Which is mg, but m here is 10, right? So this is equal to 10g. So let's rearrange here and solve for y. So y here is equal to, so I get 10g minus t cos 30 degrees. Okay. Now, at this point here, it's probably easier to give t in its exact form, right? So that would be 20g over sine 30 cos 30. So that's root 3 over 4. I'd get 80g over root 3 there. So t here is, what did I just say? 80g over root 3. Yeah, perfect. So this here is the tension in its exact form, right? And like I said, you could have given the answer at the start. That's also fine. But it's easier here to work through part B with the exact form, okay? So what we get here then for y is, I've got 10g minus here t, so that's 80g over root 3. So 80g over root 3 times cos 30, which is root 3 over 2, right? So root 3 over 2. The root 3's here, just cancel. I get 80g over 2, which is 40g. So 10g minus 40g here gives us minus 30g there. Right, so like we said before, because this here, this force is negative, I've guessed incorrectly here. So y actually acts downwards. So y acts downwards. And that's fine, right? Even if you guess incorrectly, it doesn't matter. Like we say, it's just negative as opposed to positive. So y acts downwards. We now want to find x here, this horizontal force. So to do that, let's just resolve horizontally, right? So resolving horizontally here, taken to the right as positive. So in this case here, nice and straightforward then, all I simply get is x is equal to t sine 30, right? So x here is equal to t sine 30 degrees. Okay, again, using the exact form here of t, x is equal to, so I get 80g over root 3 times sine of 30 degrees. So that is a half, right? So times by a half. So what I get here then is 80g over 2 root 3. That just cancels to give us 40g over root 3 there. Okay. Now, what I want to do here, again, is just use some basic trigonometry. So tan theta here. So tan theta is equal to y over x here, right? This vertical force over my horizontal force. So y over x, then what do I get here? So we take this positive, by the way. So y here is 30g. I get 30g over x, which is 40g over root 3. 40g over root 3. It looks a little bit messy, but that's fine. We'll just clean this up a little bit here. So I can times through here by root 3 with the numerator. So I get 30 root 3 g. So 30 root 3 g over 40g. We can cancel these g's here. So I get 30 root 3 over 40, which just cancels to give us 3 root 3 over 4. So 3 root 3 over 4. Okay. So we're nearly finished here then with part B. As you can see, we don't have a whole lot of room here. So let me just quickly finish this over here. So part B still then. We've got tan theta. So tan theta is equal to 3 root 3 over 4. So what we want to do here is just solve for theta, right? We're looking to find the angle. So theta here is equal to tan inverse of 3 root 3 over 4. Just put this here then into your calculator. And if you do this correctly, what we should get here is 52.4 degrees there. Okay. Now, just need to be slightly careful here. We need to actually describe the direction of the force exerted by the wall on the beam at A. So this is 52.4 degrees below the horizontal. So below the horizontal. So below the horizontal and away from the wall. And away from the wall there. Okay. And there we have it then. Bosh. Beautiful. Like you can see, questions like this, there is quite a lot going on, and it is very, very easy to make a mistake. So just take your time, look for it slowly, just be very, very careful and methodical. But hopefully, my solution here, my demonstration, has helped to illustrate how you would solve a question such as this one. Right, and then finally to finish with here, we have part C. So for part C then, it just says if the rope were not modeled as being light, state how this would affect the tension in the rope. You should explain your answer clearly. Right, I don't have a whole lot of room here, so will I manage to fit this all on? Maybe, maybe not, but I'll try and just explain it anyway. So in this case here, if the rope was not modeled as being light, then what would happen is the tension would increase as you move from C here to D. And the reason for that is because as you move up this point of rope here, or as you move up the rope, each point of rope has to support the length of the rope below it. Okay? So all I'm going to kind of quickly say here is the tension would increase. So the tension would increase as, how do I explain this here? So the tension would increase as you move from C to D. And how do I explain this quite succinctly here? Basically, as I said before, each point of rope has to support the length of rope below, which I don't really have quite enough room to kind of explain here. So you'll have to just take my word for it. I will include it on the mark scheme. So if you want to see the full kind of written solutions, please do check those out. But there we have it then. So the tension would increase as you move from C to D, as each point of rope has to support the length of rope below. That's absolutely fine, right? I'm not going to go into too much detail. That's absolutely fine there. So there we have it, guys. That brings us to the end then of this mock paper here. This was Set C paper 3. Hopefully you have found this paper and the video solutions helpful in your preparation then for paper 3, the applied paper right for Edexcel. So before I kind of conclude the video here, all I want to say then is best of luck for paper 3 coming very, very soon. As always, if you do need any more A-level maths revision, please do go to our website, AJMaths.co.uk. We've got Set A, Set B, so there's 3 now, paper 3, so 3 applied papers, if I've explained that very well. I don't know. I'm tired. It's been a long paper. And I do appreciate that this paper here has been very, very long. So if you made it all the way to the very, very end, thank you so much for watching. Again, I do appreciate each and every one of you that does watch these videos. So at this point here, I'm kind of just yapping. So there we have it. That gives us the video solutions here for Set C, paper 3. As always, thank you so much for watching.